Hi. So today we're gonna have a quick recap on the Monte Carlo method and dynamic programming and temporal difference, those three fundamental algorithms that we introduced previously, and then based on those, then further develop two new things for today, which is called SARSA and Q-Learning. Okay, and all of those mentioned today, those are very important and fundamental algorithms in reinforcement learning problems, and most of the more advanced or more sophisticated methods are basically all based on those very fundamental things. Okay, good. So let's have a first quick recap on the MC, DP, and TD. So we know that TD is a method based on MC and DP. Okay, so it's sort of a combination of those two. So let's try to represent the value function, okay, and to see the connections between those different estimates, okay, of the value function. So we know that the value function will be expectation over um, the future reward, right? So that would be the discounted future rewards, and that could be represented by the following expressions if we further expand those, okay, and then if we combine all those future ones, okay, into the one using the v pi with s plus t plus 1, and this will be the estimate for the value function for TD, okay, and the first one was for the Monte Carlo, okay. So remember that in Monte Carlo we have to have determination for the episode, right? So after that we can collect the reward and compute this value and update that. But TD or dynamic programming, we do not need to wait until it finishes, right? So we can do that in the middle of those episodes, and here this would be the estimate for this value in TD, and essentially, so this the last one will be for the DP. Okay, so in DP, in dynamic programming, we must know or it must require a model of the world for the transitions. Okay, so which is this probability function here, density function. Okay, so when we're saying that this doesn't require a model of the world for the transitions, so it does not sample. Okay, so it simply requires the whole dynamics or the whole transitions with all those probabilities. So it's sort of given, right? And you know all those parameters or you know all those probabilities, and you just plan ahead, okay, for the whole episode. And this is sort of just a planning problem, okay, for the dynamic programming. Okay, so for the DP and TD, so they're both bootstrapping, okay. So the reason that recall that the bootstrapping was essentially just saying that we're using the estimate of the V to update another estimate of the V. Okay, so that's sort of it's bootstrapped or bootstrapping. Okay, so that is both used by TD and DP, because here we will have this using this old V pi to estimate this new V pi, and here it will be the same for DP. Okay, so and of course Monte Carlo, it doesn't have any bootstrap because this will be essentially the true value of this RT. Okay, so there will be no estimate inside of this RT. Okay, so this is the aspect of bootstrapping. Okay, and we know that for MC and TD, okay, those two, they are model free, right? And DP, it is not model free. It requires some Markov model. So MC and TD, they're model free, so we do not require any model for that. And we just sample, okay? So the sample here, it simply means that we look ahead for a sample, for a sampling or for a sample successor state or for the next state. Okay, so we sample this tuple st, at, rt, and st plus 1 simply from some experience or from some memory. Okay, so that's it. So, and those can be discrete and they can be disconnected, right? You can just sample like maybe T1, A1, R1 as 2, and later you can sample like T10, A10, R10 as 11, right? So those can be just disconnected. This is called sample, okay? And accordingly, those this tuple includes the RT, right, and ST plus 1. So for the MC, we simply have this the whole sample, right? Because you're going to sample the whole episode, and this in TD you for each time step you're gonna sample this one transition or this one tuple, right? Like including those elements in this tuple. Okay. So this is called model 3 for MC and TD, and those are the connections and the differences and the similarities between those three algorithms. Okay, and that'll be a quick recap of what we did earlier. Okay, so and now let's have a discussion on the prediction and control. Okay, so later we're going to introduce a concept of control, and previously we have discussed predictions. Okay, so what is a prediction? So prediction is a problem that where we are given some policy pi as of this probability, this policy. Okay, so we're given this policy and we want to evaluate how well this policy performs by predicting the expected total reward. Okay, so in this case, we're gonna compute the state value function, which is v pi, okay, given some policy pi. So that's the prediction problem, okay? And in contrast, sometimes we want to have some control problem. So in control, we're gonna find the optimal policy is pi. So in this case, we're not given some policy. We're our purpose or our goal here will be to find such optimal policy pi. So that'll be maximizing the expected total reward from any given state. Okay, so predicting and control, they're very closely related, but they're talking about sort of different aspects of the same thing, right? So it's just two different kinds of problems or two kinds of tasks that we're often see in the algorithms. Okay, just some two of different perspective of looking at the same thing. Okay, good. So for example, okay, so in the in the prediction, right, for the Monte Carlo method, so we're gonna use the given policy to help us to evaluate this v pi, right? So we're gonna update or we're gonna evaluate this v pi. So that'll be this target, okay, that'll be the actual return following some state st, okay, and this will be the original v pi of st. So that would be the updating rule for MC for this value function. And how do we do that in TD? Okay, so remember that in TD, and we have just done that right earlier today. But here in TD, we'll simply update that using the temporal difference, right? So the target will be this part. That will be the immediate reward plus the estimate future return, right? And that is bootstrapped using something that we already estimated, right? So use the estimate to help to estimate the next v. Okay, good. So those are called predictions. Okay, good. So next we're gonna talk about control. Okay, so and that leads us to a new algorithm. But this is not completely new, but it's very closely related. Okay, so we're gonna talk about this SARSA. Okay, so SARSA is just a short for state action reward next state next action. Okay, so this is just an abbreviation for this SARSA. So SARSA is just so-called on policy, and it's a TD control. Okay, so we already know that control is just to find some optimal policy, right? So what do we mean by this on policy? Okay, so later we'll see this more clearly. So on policy, in short, so it means that when we're talking about on policy method, here we are updating the queue using the queue with s prime with the next s and next a next action. So then the important thing is that next action that is derived from the current policy. Okay, then this is called on policy. But if that next action is not derived from the current policy, instead, if that is derived from some greedy policy to maximize the queue, and that would be called the off policy. Okay. All right. So let's forget about it for now and just go ahead with this updating rule for this SARSA. Okay. So here we're gonna so this would be the TD control. So it'll be just simply based on TD, right? Everything looks like TD. So here, the only different thing is that we're gonna update this queue, okay, instead of the V. So after every transition, so we're gonna update the queue. So this queue STAT, that'll be updated using this rule, and where this is exactly very similar with TD, right? It's just instead we have this queue here rather than the V. And we said that using this as t plus 1 and AT plus 1, and that is called on policy updating. Okay, so the next action AT plus 1, that is derived from the previous queue, and this is important. Okay, and it's we call this on policy because it's updating the queue using the queue of this would be just S prime or ST plus 1. Okay, so we use those terms interchangeably. And then this A double prime, that would be just for the next state, next action. Okay, this is not next action. So this is just to distinguish this with the other one we're going to introduce later. And this is still the AT plus 1. Okay, this is ST plus 1. So that is from this next action that is still from the current policy. Then in this case, we can call this on policy updating. Okay, so in the on policy updating, we assume that the current policy is to be followed. Okay, so we still use the current policy to make this action. Okay, and we will see later that in Q-Learning, very shortly, that is using the off policy. Where in the Q-Learning, in the off policy one, that we're going to have that next action that is always using the epsilon greedy or E greedy, which always tries to maximize the queue in this updating rule. Okay. All right. So that'll be the SARSA. That's just some on policy TD control, the control version of TD. Okay. Good. So the next one will be this Q-Learning. Okay. And the Q-Learning, in contrast to the SARSA, so Q-Learning here, it'll be the off policy TD control. Okay. So, and again, it will be very similar to TD, but here, the only difference to SARSA, that will be this off policy part, right? So here, how do we choose this next action, A prime? And that has to be, so in this algorithm, that has to be some action, A prime, that can maximize this queue, okay? So here, when we're updating this queue, we're simultaneously to choose some A to maximize this queue at the same time, right? And that is called off policy. So at the same time, when we are trying to select some action A prime for the next state, ST plus 1, at the same time, we are actually already updating or already like deviating from the previous policy, right? So we're already trying something new. or not something new. It's just trying to maximize the Q. It's not trying something new. Okay, it's still using trying to use the greedy action. Okay, so that is why we're calling this as the off policy. Okay, instead, if this was on policy, then we wouldn't have this to maximize the Q here when we're updating this Q. We would just follow the previous Q as we did in SARSA to try to compute this Q using the old policy. Okay, but here we're gonna select already. So we're already going to select this some new action A prime for the next state to try to maximize this Q at the same time, and that'll be call this off policy. Okay, good. So our policy is updating the Q using the Q of S prime and some greedy A prime. Those are also talking about ST plus 1 and AT plus 1. Okay, where this A prime is chosen to try to maximize the Q. Okay, and it assumes a greedy policy is going to be followed. Okay. All right, so here I had another note is that, however, a good agent or a well-trained agent, it also needs to explore new things sometimes, right? It cannot, so a good agent, it cannot enjoy the greedy policy or greedy strategy all the time, right? So and this agent has to take some actions to in the greedy policy. This agent simply take the actions that maximize the Q all the time, right? But here, what I mean is that sometimes it is not a good idea to always to implement this greedy policy, right? To maximize this Q all the time. So sometimes we have to choose to not maximize this Q. So that's why we were taking the probability of having either having some maximization here or not. Okay, or just try to randomize. So that'll be something later, but not for today. Okay, good. So, and the last thing I want to talk about for today, that'll be this actor-critic architecture. Okay, so, and we can already see this architecture in the TD learning. Okay, so you can see from this little diagram is that, so the environment gives this state, and that'll be taken into this critic, which is the value function, and vector, which is the policy. Okay, so, and this actor, the policy, outputs some action, and that action will affect the state, right? Affecting the environment for the next state. So, and also the environment gives the reward, right? So the critic here, the key part would be this critic, right? So the critic is essentially just a state value function. Okay, and here it has this sort of the so here that'll be just the evaluation here, that would be just simply the TD error. Okay, in this case, for the TD learning, and it has, so this sort of the actor-critic architecture, it has a explicit representation of policy and value function. Okay, and the critic here, it drives all the learning, and we have the on-policy method. Okay, so, and more details. Okay, so first is that the critic is a state value action, as we just said, and after each action selection, the critic evaluates the new state to determine whether the things have gone better or worse than expected. Okay, and then the evaluation here, that'll be simply the TD error. Okay, as we see before. And now we suppose that the actions, they can be stochastic, right? And it's given by some, let's call this as some preference function, some P, okay, taking S and A. So this stochastic policy, that'll be the probability of having this A given some S, and that'll be the fraction, the proportion of this E to the power of this P, and over the summation of all those E's. And then what we can have from here is that to strengthen or to weaken the preference, this P function, and this thing depends on this TD error, right? So then we could update this function P by using the TD error with some parameter beta here. Okay, so some advantages for this critic architecture first is that there will be a minimum computation to select the actions, right? So because there will be no need to search the whole action space, and especially for a very large action space. Okay, and it could also learn some explicit stochastic policy, as we mentioned here. Okay, and so that'll be everything for today. And so today we had a quick recap on the Monte Carlo and dynamic programming and TD learning. And then we, based on the TD learning, we had a on policy and off policy controls, just as the SARSA and Q-Learning, right? And that'll be all for today. Okay, good.